Welcome to my CompTIA Network Plus N10006 study material. This is Chapter 9, Network Optimization. In this chapter, we're looking at things like high availability, QoS, and we're going to end with a small case study on a SOHO network design. So, for high availability, we're going to be talking about network optimization, and that means optimizing performance. So why is high availability a requirement in today's modern network designs? And what mechanisms can be put there to provide or improve network high availability? What are some various technologies for optimizing network performance? What is QoS? What does it mean? And how can we take what we've learned so far to help design a better SOHO network? So high availability measurements. Normally we're talking in terms of uptime, meaning if we want uptime within a year, 5 nines, we can represent these in different forms of nines. For example, if we're looking at 5 nines, 99.9999 uptime, we're looking at around 5 minutes and 15 seconds of downtime per year. So, quick little chart. If we're looking at 4 nines, so 99.99 uptime, we're looking at 52 minutes a year. If we're looking at 99.939, we're looking at 8 hours 45 minutes. If we're looking at just 99% uptime, we're looking at 87 hours of downtime and 39 minutes. So the different variations of nines do matter. That's why we build in things like fault tolerance and high availability. So a single point of failure with some redundancy could be things like link redundancy, where important. Maybe multiple connections between switches and routers. We could also be talking about internal redundancy, things like hardware redundancy. Maybe if we have important switches with dual power supplies. The key here is no single point of failure, meaning every key component has a component redundancy, meaning we have multiple routers, multiple switches, as well as multiple link redundancies. So things like redundant networks with a single point of failure could look something like this. It is single network devices with multiple links. We could change that up with no single point of failure with multiple pieces of equipment. That way, every type of network device, except the end ones, should be able to recover from any type of failure. Things like hardware redundancy could take the form of things like multiple NICs. Something like an active-active, that's where both NICs are active at the same time, each with its own separate MAC address. That makes things more complicated. We could do active standby. That's where we have two NICs where one NIC is active at a time. So if one NIC fails, the other one kicks in. But then you end up with more weight on one than the other, meaning one NIC could be on for multiple years, where the other one is idle, just waiting to jump in when the other NIC fails. Some of the other areas that we are talking about could be layer 3 redundancy links. Normally that's going to be in terms of like a router redundancy. Two big ones are HSRP, which is Cisco proprietary, and that's going to be an active standby, but it allows for a virtual gateway. That way, whoever is hosting or is active with the virtual gateway, it allows for an access or an egress point or default router. Another one is a commonly addressable redundancy protocol, or CARP, which this is going to be the open standard version of HSRP. Again, we have a virtual router. So this may be the active router, so it's going to have the settings for our virtual router. If that router goes down, the standby router becomes active and it takes over the virtual router. That way our gateway is actually going to be our virtual router's IP address. Now there's other forms of this. There's virtual routing protocol. There is virtual router redundancy protocol, VRRP. There's also a gateway load balancing protocol, GLBP. Each have their own pros and cons. So it's going to be the virtual or first hop redundancy or our egress point redundancy is going to be based off of what technologies we have. Next, we're talking about link redundancy. We could do what's called LACP, or Link Aggregation Control Protocol. It allows us to do bonding or load balancing between multiple links. And that allows all three to be very similar. Sorry, all four links in this example to be very similar. They're going to act as one. And that's very similar to something called Ether channel, which does the same thing, as well as port aggregation, or PAGP. It all depends on the manufacturer of the hardware that you're using. Moving on is our considerations for our high availability. Could be things like chassis redundancy, software, protocols, what features, what are the infrastructure devices needs, are there environmental examples or environmental conditions or concerns. For example, if we have a building, if we have fiber coming in from one side, can we have fiber coming in off the other side of the building? That way, if something happens to that strand of fiber, we have backup fiber. That could be environmental. That's a very common concern. We had road construction at one college, and while they were digging up the parking lot, they cut through the fiber that we had to our facility, then terminating all internet connectivity with our campus. So best practices for high availability: look at the technical goals, look at the budget, perform some type of business impact analysis so we can categorize business applications, establish performance standards for our high availability, define how we're going to manage and measure our solution. Another item could be content caching. This is a big one. Content caching is a network appliance that can receive and then copy content. That way, if it notices lots of people are accessing Facebook, it may then download large chunks of Facebook so it doesn't have to keep querying Facebook's servers. There may be a delay, but content may be on site. Makes it a little bit easier, especially if you have slow internet. Or what if you're on a submarine? It's not the same as a content engine, but very similar. You're going to have a resource that will download snapshots of common web pages at that specific time. And that way, when you're submerged, you still have a portion of the internet that you can view. It will only be that snapshot in time, but it's something. We have load balancers, and content switching allows the request coming in from a server or server farm to be distributed across multiple servers. Normally, this will be looking at the identical or the same content. Google. You go to google.com. In reality, this is load balancing. This is actually over hundreds of servers, if not more, that are all identical with content, but that way the load is not based off of one server. Here's an example. We may only see one server, but in reality, it's a server farm with hundreds of servers, if not thousands of servers. Next, we have what's known as quality of service, or QoS. And this essentially allows us to place priority on traffic. Basically, it allows us to strategically optimize network performance for certain types of traffic. If we want to identify traffic that's important or that's going to need a higher priority, we can do that with QoS. If we are looking at things such as bandwidth usage, maybe we are going to allow certain items more bandwidth than others. We could do that with QoS as well. Essentially, QoS allows us to efficiently manage our bandwidth of our network based off of prioritized needs. Categories of quality issues, there are three major types: delays, jitters, and drops. Jitter is uneven arrival of packets. Delay is time required for the packet to travel from source to destination in a timely manner. And drops are just when a link is just so congested, it just overflows and it starts dropping or removing packets. So effective bandwidth could be understanding how we're going to get from A to B, looking at the weakest links, and figuring out how to best send data. So QoS configuration, normally we're looking at various types of traffic. Normally we categorize it based off of performance requirements. For example, voice and video have a real-time component. Voice specifically. Video if you're doing video conferencing. But I mean, both of those, the performance matters. Where data, not so much. Second category is maybe categorizing it into two specific types of categories: low delay and low priority. Next is the documentation of our QoS policies so that we can make those policies available so that people know the appropriate response or services off of certain types of traffic. Knowing that even if you have data, the voice is going to take precedence. So if your data is degraded, it's going to be a sacrifice for our voice. QoS has three common components: best effort, integrated services or INTSERV, or differentiated services, DISSERV. So best effort treats treatment of the traffic, doesn't truly provide QoS to that traffic because there is no recording or reordering of packets. Best effort uses first in, first out. Or integrated services, INTSERV, is often referred to as hard QoS because it can make strict bandwidth reservations using signaling among the network devices to reserve bandwidth. Key thing here is it can reserve bandwidth. The differentiated services, or DiffServ, allows for the differentiation between multiple traffic flows. Specifically, packets are marked, and routers and switches can make decisions based off of those markings, often called soft QoS. So normally it's best effort, DiffServ, then INTSERV. Best effort, there's no restricted. DiffServ is less restricted, and INTSERV is the most restrictive. Our QoS mechanism deals with classification, marking, things that will help with congestion management or congestion avoidance, shaping and policies, as well as link efficiencies. So classifications. We could classify things based off of protocols: POP, IMAS, SMTP, Exchange. The classification does not alter any bits in the frame or packet. It just separates traffic into different categories. Markings could be an actual altering bits within a frame or packet or segment that will tell the network how to treat it. That's going to be a hard QoS. and then you set the precedence or QoS numbering. Congestion management is when a device receives traffic faster than it can transmit, so it'll buffer, and that's going to be that buffering process is called queuing, and the queuing algorithm empties the packet in a specific sequence and amount. Normally, that exiting of that queuing could be one of three types: weighted fair queuing, low latency queuing, or weighted round robin queuing. So, examples for our queuing could be things like priority queuing, business queuing, application queuing, or best effort. So, essentially, as these different queues start filtering up or increasing, we can have the egress change depending. We could have round robin, so it goes from one to the other, to the other, to the other, and then back again. And so it takes one for each one. We can put weights so that these two may be weighted heavily. So it might take one from here, two from each of these. So, I mean, our queuing examples can change depending on how we have it configured. Congestion avoidance, we could have a technique called random early detection, and that introduces the possibility of a packet discard as queues start increasing. So essentially, as links start getting overloaded, we can start discarding packets. So we actually set a threshold for a min and a max, and if anything is hitting that maximum threshold, we can start deleting or dropping packets as needed. We could have things for policy and shaping. Policy or policing our things could also be, again, discarding packets after we get a certain rate or certain level. Shaping could then, before we get to end devices, we could actually shape or buffer from slower devices first. That way we can actually start setting link rates. That way we can make sure that we are getting items at the appropriate speed for us to be able to process and have them egress. Link efficiency, this is an important one, is on the slower speed links, we could implement compression or link fragmentation and interleaving to make the most of our limited bandwidth. Compression is going to be trying to compress data in such a way for us to send more data. So that compression is, it will compress a packet's payload or header to conserve the bandwidth. That way it can use like RTP header compression to reduce a VoIP header from a 40 byte to maybe a 2 or 4 byte header. It could also do what's called link fragmentation and interleaving. That's going to be fragments to a large data packet and interweave smaller data packets between the fragments. All right, let's get into our case study. Our objective here is to create a network design that will meet the collection of criteria listed below. So we need to meet all requirements. We need to talk about media distance limitations. We need to look at maybe network device selections, things like cost and things like that. Look at environmental factors as well as compatibility for existing and future equipment. Meaning, if we have a distance between a building, what media might we use? What are the distances that we know that we may need to use? If we're looking at Wi-Fi, do we have to talk about antenna types? So here's our case study. We have two buildings. They're over 1 kilometer apart. Building A is our internet provider. How do we design a network that is going to be fully redundant between A and B and still allow all traffic from B to get through A? How do we get the buildings connected? How do we provide Wi-Fi throughout the facilities? So think about that and try to answer that. That's actually all I had for this chapter. I want to thank you.